Hello, everyone. My name is Samala Minashari. I'm a graduate student at Tennessee State University. Today, I'm going to present a research study about homogenization-based optimization of lattice structure using granular micromechanic approach under the advising of Dr. Ranganathan Partharasi and with the help of my colleague Kehinde Omotayo. At the very beginning, I want to introduce the concept and then explain the methods of homogenization, following by granular micromechanics approach, and then explaining the result and at the end, the conclusion. Let us look at some material properties charts here. For example, strength with density or Young modulus with density, we can see that metal occupy the top right hand side corner as expected. The foam occupy the bottom left hand side, and in between we see the polymers composites and so on. The lattice structure have great potential to occupy the unfilled area, such as the top left-hand area. In the history of material, primarily, the desired material behavior is obtained by modification of either the chemistry or the microstructure or the architecture. For example, we can see backlit, which was one of the revolutionary polymers, as an example of modifying chemistry. In metal alloys, very often, the material properties can be tuned by modifying microstructural features such as grain size, defects, and etc. With the advances in additive manufacturing, we can obtain desired material properties by modification of lattice architecture. Now, the question is how to connect overall material properties to lattice structure. One of the methods by which we can make this connection is homogenization. In this procedure, we convert a lattice material with complex architecture into homogenization-based uniform material, which is a homogenized uniform material, which is expected to have the desired mechanical properties. The main determinant of the macro scale material properties are the architecture geometry and the material of the lattice member. Why do we need the homogenization? There are two main purposes. One is that homogenization allows us to greatly reduce the computational cost of analyzing a structure, such as a building or a frame which is made of lattice material. The second reason is that homogenization allows us to obtain closed form relationship which connects the macro scale material properties with the lattice architecture and material properties of the lattice material. Right now, we want to predict the macro scale properties from the lattice architecture. Eventually, we do want to get to a point where given the target mechanical properties at macro scale, we are able to identify potential lattices which are best suited for the target properties. This is the engine of our homogenization approach. We do it in 4 steps. In the first steps, we identify the RVE for our lattice architecture. RVE is representative volume element, which is sufficient to represent the behavior of the periodically repeated lattice. We prescribe a boundary strain on our RVE. In the second steps, we connect the applied boundary strain to the individual stretches and relative rotation of the lattice members. For this, we have tried both affine and non-affine approaches. In the next steps, we use the constitutive laws for the individual members to obtain member forces and moments. Finally, we use the principle of ritual work to calculate the stress tensor. According to us, how we connect the macro scale boundary strain to the lattice member deformation is a key aspect that determines the accuracy of the approach. We note a particular point here that the affine deformation, but not for bending dominated lattices such as here. For the bending dominated lattice, using affine deformation gives an overly stiff and unrealistic response. Therefore, we introduce and calibrate a strain concentration tensor. We use a novel approach to compute our strain concentration tensor for bending dominated lattice when all joints are treated as hinges. A lattice becomes a mechanism whose behavior can be predicted in a straightforward manner using geometric compatibility. When the joints are perfectly rigid, the affine deformation works fairly well. That is, the strain concentration tensor is an identity matrix. For all cases in between, we use linear interpolation. See from the equation now the relative rotation and the individual member strains are obtained from the boundary strain. To obtain the stress tensor from member forces, we use the principle of virtual work. In the first equation, we can see that the total virtual work in the macro scales is equal to the virtual work on each member due to the stretch and due to relative rotation. Substituting the macro scale to the lattice scale deformation relationships, we can obtain a formula for stress tensor. You can see here, this is the stress conjugate to strain, and this is the stress conjugate to the rigid body rotation for members. At this point, I would like to mention that all of these is quite recent work that we have done. The formulation is simplified for the case of plane stress so that we can apply to the 2D lattices. F here is force at nodes, and M is moment at the nodes, and the MU is the stress conjugate to rigid body rotation. As I have mentioned earlier, the micromechanics-based approach is simpler to implement and provides close form relationship as opposed to full scale finite element approach. However, we need a good micro transition scheme for it to work well, especially for bending dominated lattices. The affine approximation is very far from the actual deformation. This is the compliance tensor for plane stress condition. All of our structure are studied in plane stress condition. No other plane stress like in Z direction here. We compare the result of our micro mechanics calculation to finite element calculation using Abacus software for 2D. The connecting element have 0.5 millimeter radius and 1 centimeter length. Only the bending stiffness of the member resists relative rotation at the nodes. Since the members are cylinder, the axial stiffness is dominant. Therefore, the Poisson's ratio obtained are close to a hinged case or a mechanism. Here is the result for diamond lattice from Abacus finite element analysis. The Poisson's ratio, as expected, is for a mechanism, which is 0.99. And here is the result for hexagonal lattice from Abacus finite element analysis. Again, the Poisson's ratio is close to that expected for a mechanism, which is 0.96. And this is the result for reentrant honeycomb. As expected, we get a negative Poisson's ratio, and the lattice is much softer from either the diamond or the hexagon. Here are we compare the finite element result to the micromechanics result. I want to highlight a point for the hexagonal lattice. We can see that using the affine approach gives much higher elastics moduli and much lower Poisson's ratio than the finite element calculation, which we assume to be accurate. However, using our novel non-affine macro transition, we are able to get much better results. We are still working on the micromechanic calculation for the intra-honeycomb. This is the main calculation using MATLAB software. As you can see, the 3x3 matrix from obtaining the volume here is RVE, K is the stiffness, and R is the length of each member. The values for all parameters and the compliance tensor is in 1 over megapascal. And here is the effective elastic properties for the lattice in plane strain. In conclusion, the developed micromechanics approach is satisfactory for both stretch-dominated and bending-dominated lattices. The derivation have been developed for a general 3D case, and the approach can close form a compliance or elasticity tensors and is lattices. The approach is worth exploring for target material properties. And now at the end, I want to have a special thanks to Dr. Anil Mishra from University of Kansas, who always helps us with research, and Dr. Lee from Tennessee State University in Civil Engineering section for giving me and my colleague the access to software like ABACUS and MATLAB. Finally, we thank the Granular Mechanics Technical Committee for the opportunity. Thank you. Have a nice day.